Introduce today's speaker of the TAP Colloquium, Tanvi Karwal from the University of Pennsylvania. So Tanvi got her PhD in 2019 at the University at Johns Hopkins, together with Mark Kamiankowski, and has been a postdoc at the University of Pennsylvania since. She's a phenomenologist in cosmology and mostly interested in figuring out what other fundamental physics explanations are there, except for lambda CDM, for the accelerated expansion of the universe, and what kind of new physics can be discovered given the tensions that we see nowadays in data already. And so today she's going to talk about how fast is the universe expanding and why. And I look forward to the talk. Please take it away.
Okay. Thank you so much, and thank you for having me here. This talk is based on work done with a lot of people. I'll just highlight two names, Kim Berghaus and Alexa Bartlett, because both of them are on the job market for a postdoc and for grad school, respectively. They're excellent. Please keep an eye out for their applications. But let's start by talking about how we think the universe has expanded. So the very young universe was, of course, in this hot, dense plasma. And as the universe expanded, it cooled. And eventually, protons and electrons could combine, but because we're cosmologists, we want to make everything more complicated. We call that they recombined, and the universe became neutral, and the cosmic microwave background was emitted, which is the oldest light in the universe. The universe has since continued to expand, and today's universe is expanding with some current expansion rate that we have a few different ways of measuring. You can measure it based on the very early universe, with assumptions about cosmology, or you can measure it somewhat more directly in the late universe with some astrophysical assumptions that go into it. The really interesting thing is that these two estimations of the Hubble constant do not match, and they're now mismatched at 5 sigma levels. This is very interesting. We call it the Hubble tension, and my talk today will largely be about that. I'll tell you about the two different ways in which we measure the Hubble constant, which leads to the Hubble tension. Because I'm a theorist, I look at this and I just think, yay, new physics. So then I'll tell you about what a new physics solution to the Hubble tension should look like. I'll give you one specific example of it that I've worked on extensively, the early dark energy solution. And then we'll talk about what challenges the solution faces and how we might find a model to replace lambda CDM for cosmology. Okay, so let's start by talking about the Hubble tension, specifically talking about how we measure it with early universe cosmology. So this is a temperature map of the oldest light in the universe, the cosmic microwave background. The hot and cold spots on this temperature map correspond to density perturbations. Density perturbations the same as sound waves. So this imprint was essentially produced by sound waves in the very early universe. And if you look at this map, you might think, oh, there's like a preferential patch size on the map, and you would be right. This map has scales preferentially distributed at about 1 degree on the sky. So 1 degree scales, you would have maximal variation in this map. And that corresponds to the farthest distance that sound waves travel in the early universe. So you have the very early universe, you have your inflation ends, and you have this universe full of plasma. From that time on, till the time that the cosmic microwave background was emitted, the universe had plasma, and that had sound waves. So that entire time is how long sound waves had to travel, and this is the farthest distance that they could travel. That is what gives you this maximal variation in the CMB. So this is a slightly complicated picture. It doesn't actually get less complicated. In order to extract cosmology from the CMB, we need to assume a cosmological model. That's the only way you do it, because the CMB is a fairly interesting but very complicated data set. Here's our standard model of cosmology. We call it lambda CDM. We think the universe has broadly these three things. We think it has matter, radiation, and dark energy. In terms of lambda CDM cosmology, matter's energy density just goes down as redshift cubed. So redshift is a linear length scale. So if I have a universe of this size and I stretch it out to double the size, now you're at a redshift of 2. So it's just a linear length scale. Now, if I have, say, 3 stars in my universe and my universe's box becomes larger, so the volume has increased. But the stars, the number density stays the same. So essentially, matter density just goes down as volume. That's why it's redshift cube. Radiation gets an extra factor because when the universe expands, it stretches out the wavelength of a photon. If you have a photon of a longer wavelength, its energy density goes down, right? Basic physics. So with that, we have matter and radiation explained. But dark energy is a weird one because its energy density, sorry, this is energy density versus redshift. Its energy density just doesn't change. As the universe expands, there's just more dark energy. It's really weird. Under lambda CDM, we assume this is a cosmological constant. And that's what that means, that its energy density just stays constant. So using these components in the universe and using GR, which tells us that the expansion rate of the universe throughout its history depends on the energy content of the universe, we can go back to our map and figure out that today's universe should be expanding at some specific current rate. That number is measured by the Planck satellite experiment, which is also a full sky map of the cosmic microwave background. Looks pretty similar to this, but they have a different color scheme. Don't worry about it. Unimportant. Anyway, they measure that number. So this is based on the very early universe. Why can't we just see how fast objects are receding away from us? That would be a much more direct measurement. And we absolutely can do that. For example, using the distance ladder. So from the Earth, we can look within our own galaxy for stars called Cepheids. Cepheids are stars of a standard brightness. So we use like parallax to figure out how far a Cepheid is within our own galaxy. Just because, it's close enough, we can still use parallax. Now we know how far it is and we know how bright it is. We can use that to figure out how far a dimmer Cepheid is in a different galaxy. So now we have a distance to this galaxy. We use galaxies that also host type 1a supernovae, also objects of standard brightness, but much, much brighter. And then we know how far these supernovae are and how bright they are. And so we can figure out how far much further away supernovae are that are much dimmer. The reason that we want to go out all the way to really far out distances is because we want to make sure we're actually measuring the expansion of the universe and not just peculiar velocities of galaxies, right? So we go really far out. We have measured the distance to these supernovae. The other thing we want to know is their recession velocity, which we get from how their spectrum is redshifted. And now we can figure out how fast the universe is expanding. Again, we do that, for example, the SHOES collaboration does that, and they find this number. So we have measured the expansion rate of the universe twice now. We used the late universe and astrophysical assumptions. We used the early universe and cosmological assumptions. And here is where you have the Hubble tension. Now, you can obviously look at this and say, come on, somebody messed up. Somebody didn't fix the systematics in their data. And that's a great question to ask. It could be that the Hubble tension still disappears. It could be something that we haven't thought about yet to clean our data for. But the really interesting thing is that it's present in several other data sets. And it really looks like it's a mismatch between the early and the late universe. So here I'm showing you a whole bunch of probes that again rely on the lambda CDM model and look at the early universe. These don't rely on a lambda CDM model for the large part and look at the late universe. If these two measurements agreed, early and late universe agreed, you should be seeing cross scatter, but you don't. So maybe something interesting is going on. Okay, if something interesting is going on, maybe it's new physics. So is it that lambda CDM is wrong? And if it is wrong, how do we figure out what this new physics should look like so that we can go ahead and solve the Hubble tension? That's what I'm going to talk about next. But if you have any questions, let me know.
I guess if you go back to the plot on the previous slide, that's possible.
Yes. Yeah.
Oh, that one. Right. So I guess just to make sure I'm understanding. So the point is just that, like, rather than trying to go through all the weeds of like all the systematics analysis that people have done, the point here is just that, like, there's so many analyses that have been done with the late time data, and except for like this one outlier,
yeah,
they're largely not consistent with what we see from the indirect.
Yes, yes.
Probes.
Not only that they're largely not consistent,
yeah,
but they all trend higher. Ideally, even if they're not consistent, that's one thing.
Right.
But the fact that they all trend higher,
I see.
that's weird. Because ideally, even when you don't have consistency, maybe someone underestimated their error bars, you should see some of these points falling lower. You should see some of these guys falling higher. But that's not happening.
Oh, okay. Yes.
Yeah. Okay, oops, went too far, sorry. Okay, so what should this new physics look like? Let's go back to thinking about the cosmic microwave background. And here is the newcomer screen. I promised you, Planck used a different one. So this is again the cosmic microwave background. And I'm again talking about that preferential patch size on CMB. Yeah.
All right, sorry, I know you moved on, but could you just go back to that point? I mean, I assume the reason this gets to 5 sigma is that all of these data sets are taken to be independent. And so then that's pushing down.
That's
it looks like just how the error bars are drawn.
Yeah.
If I just draw 2 sigma error bars, they overlap.
That's a really great question. That's not how we get to 5 sigma. If you were to do that, you actually get to above 5 sigma. 5 sigma is just the Planck CMB lambda CDM measurement of H0 and the Shoes late universe measurement. So the 2 specific measurements I talked about right before this section, just those 2 are discrepant at 5 sigma. And the reason that we think about those measurements the most is because those measurements are the most precise versions of their branches. They have been thought about the longest. They have been scanned for systematics the longest.
And where are those 2 points on this plot?
Oh yeah, great question. So the top one, that's Planck. And then whichever error bar fits this.
The rice.
Second one is this one. That'll be the 2021. That should be Reese et al., which is the right one to compare. I don't think this has that point. I'm sorry.
The Reese et al. Is the right one to compare?
Yep.
It's third from the.
Thank you. It's right there.
Yeah, there we go. It's lined up.
Okay,
Yeah.
that's the 2019 one. So this is this was put out in 2020.
I see.
The numbers that I showed you in the previous slide were 2022 numbers. That's where we get the really big 5 sigma difference. All right. Thank you. Excellent question. Okay. All right. So what should this new physics look like? Let's think about the patch size of the CMB. That patch size, it's just an angle on the sky, right? Angles on the sky are a physical object on the sky and our distance away from it, the object's distance away from us. And that's exactly what this angle is too. That's the physical size of the sound horizon, the largest distance that sound waves traveled, and our distance from the CMB. So if we think about how the universe is expanded, looking at that same plot again, energy densities versus redshift, the distance between us and the cosmic microwave background, distances in cosmology are integrals. Specifically, this is an integral over this portion of the universe, everything after the cosmic microwave background was emitted. So it's an integral over post-recombination, h of z. The numerator, on the other hand, is an integral of the other side, pre-recombination, h of z. So if we use this and know that the angle is a measurement, that can't change. The physics has to change to fit that angular measurement. We get that this angle is directly proportional to our Hubble constant and the size of the sound horizon, which tells us these 2 quantities have to be inversely proportional. If we change the Hubble parameter and we want to fit the CMB, we need to decrease the size of the sound horizon in this case. And that is actually echoed by data. I'm not just a theorist coming here and telling you guys, this is what needs to happen. It's echoed by data. Now, what I can do is I can take late universe measurements, for example, of the distance ladder. So this is like the Shoes H0, the higher one, and figure out what these predict for the sound horizon. I can similarly look at early universe physics data, even if I don't take any CMB data at all, and they all predict a different sound horizon. For reference, this is the exact opposite trend of the Hubble parameter. So it looks like what we would need to do, one, with our new physics, is decrease the size of the sound horizon to increase the predicted H0 from CMB. Because the sound horizon depends on early universe physics, we need to add new physics in the very early universe. All right? Now I've talked your ear off about the cosmic microwave background. You guys all know that's not the only data set that we have in cosmology. We have so much more information. These are just a few data sets. If your favorite one is not here, I apologize. But we have a lot of information in the later universe in cosmology, and just about all of this is very consistent with lambda CDM. In the early universe, our best data set remains the cosmic microwave background. I've spoken to you about how to stay consistent with that. But as we're trying to solve one tension, we shouldn't introduce a new one. So ideally, we need to leave the late universe unchanged so we don't create new tensions. So here's our requirements for our new physics. So let me tell you about how early dark energy embodies these requirements. Before that, I can again pause for questions. All right, so how does early dark energy resolve the Hubble tension? Let's go back to thinking about the cosmic microwave background. I just told you we need to reduce the sound horizon and do this by changing early universe physics. So the cosmic microwave background has that preferential patch size, which is the furthest distance that sound waves traveled. We need to make that distance smaller. One way to make that distance smaller is just to give sound waves less time to travel. So we need to make the CMB be emitted earlier. The CMB is emitted when protons and electrons, not neutrons, protons and electrons recombine to make the universe neutral. So maybe we need to make them recombine sooner, maybe by cooling the universe faster. One way to cool the universe is through expansion. So what I suggested was that the pre-recombination universe must expand faster. So that it cools down and the CMB is emitted earlier. And we get the, we have RS smaller than what lambda CDM predicts. Let me show you what that actually looks like in practice. If you were to just take the observed cosmic microwave background, this is also an illustration of how the Hubble tension comes about. And I force the Hubble parameter to be larger. The CMB then looks kind of like this. This very much disagrees with data. You can see that these two do not look like the same distribution at all. If I add early dark energy, which I'll get to in a moment, what I am capable of doing is reducing the patch size, the physical size of those patches. And then we come back into agreement with data. All right. So we can achieve the first part of this. For the second part, I'm going to start talking about actually what early dark energy looks like, and looks kind of like this. This is the same plot you've been seeing. So it's energy densities versus redshift. And remember that the expansion rate depends on the energy content of the universe. What I'm doing here, besides having radiation matter and a cosmological constant, I'm adding a new component, which is early dark energy, this red line. So it looks like a cosmological constant initially. You can see that this portion is parallel to a cosmological constant. And then after some time, it begins to rapidly vanish. That is, here, the curve is just going away pretty fast. So the total contribution of early dark energy over time is just this one localized peak. It does not impact the late universe at all. So the parameters of this sort of early dark energy are then how much early dark energy we have, when it pops in, and then how fast it disappears, or what is the slope of this line after that mean. Now, because remember, this is close to zero or at zero, we're also achieving the second point from our new physics. We're leaving the late universe unchanged. All right. Now, what I've shown you so far is the phenomenological model. That just means that there's no fundamental physics behind what I'd shown you on the previous slide. But this sort of phenomenology can be created by several different fundamental models. I've worked on a bunch of these myself, and I'll be talking to you about, actually I'm talking to you about all of these. But this is not the only way to create early dark energy. A lot of theorists have also talked about it. This is a non-comprehensive list. I'm sorry if I missed your favorite paper, but the list goes on and on. There's a bunch more papers that came out in the last few months that sadly are not here, but yeah. So it's an interesting thing to think about. So let me talk to you about one of the simplest kinds of early dark energy. Sorry, the first early dark energy that I have, that I worked on. It was inspired by ultralight axions, and that's the potential it had. And it was a scalar field. So here's what all of those words mean. Now, these two plots should be synchronized in time. So you can read into what is happening here as representative of what is happening here. A scalar field is just a ball rolling down a hill, or specifically in our case, a ball rolling in this sort of potential. So initially the ball is stuck at the top of the hill. You can see that moving there. And that's when we have that flat portion. Its energy density is not changing, or its energy here is not changing because it's stuck at the top of the hill. Then it rolls into the potential and oscillates around here. And that's when you get these oscillatory features. And that's when the energy density is disappearing. Does that make sense? Okay. So scalar fields are something cosmologists have thought about for a long time. They're a really straightforward way to think about dark energy and what could be producing even the late time cosmological constant. We're using it to produce early dark energy. And you can see that this early dark energy has the same features, of some amplitude, some amount, some appearance time, and then it disappears in the late universe. Yeah.
Is there a simple way of understanding what the dissipation is that keeps that motion, that damps that motion?
Yeah, that's a really good question. Okay, so those are two slightly different questions. Are you asking about what the rate of disappearance is, or why it disappears at all?
I'm saying your ball in the well, if there is no dissipation, it would just go back and forth with the same amplitude.
Yes, that is correct.
Force.
Yeah. So the dissipation is the expansion of the universe. So ideally, maybe I will try to fix this. What I should be showing you here is what the potential looks like over time.
We got a Zoom question.
Sorry, I don't have glasses on.
It's a question about the mass of the axions.
But we can only see like the first part of the sentence.
Yeah.
So
what mass
Oh,
should
okay.
the axion have to solve potential? Oh, that's a really good question. These are ultralight axions. So sorry, I'll get back to your question in a minute because this is a faster one to answer. These are ultralight axions, so their mass is like, oh God, let me remember this correctly. Like 10 to the minus 30 something EV. So they're really, really light because they have to start to roll in the very early universe. Hopefully that answers your question. Your question, on the other hand, what's happening to this potential really is that the expansion of the universe is spreading it out. So it doesn't actually stay as sharp the entire time. And that's what makes the ball not go all the way up. The Hubble expansion of the universe effectively acts like friction. And I'll show you an equation for that in a few slides. Yeah.
I'm sorry, but you're saying that as the universe expands, the potential will get shallower or deeper?
Shallow.
Okay.
No, shallow. Yeah, shallow. It just like spreads out. So you essentially.
Okay, so.
Yeah.
Okay, thanks.
All right. So with this sort of early dark energy, this is the first one we started thinking about. We then threw a lot of data at it. We threw all of the consistent data sets. So that was cosmic microwave background, baryon acoustic oscillations, and supernovae. And we also threw the local Hubble measurement at it and tried to see whether early dark energy could solve the Hubble tension. And I know there's a lot going on this slide, so let me take you through it step by step. Let's concentrate on this square down here. Here I'm showing you the amount of dark matter in the universe and the Hubble constant, because those are both parameters also present in lambda CDM. Now, this orange contour down here is lambda CDM, and these gray bands are the local Hubble measurement. And you can see they don't overlap. That's where the Hubble tension is. Now, when I add early dark energy, and I'm showing you several different early dark energies here, you don't need to worry too much about that, but you can see that all of the different early dark energies I'm showing you, one, increase the error in the Hubble constant, but two, also shift the Hubble constant. You can see that the top of this peak and the top of these peaks are different. So they increase the Hubble constant, they slightly increase the error. That combined effect means that the 1 sigma contours now intersect between these two. And so the Hubble tension is solved. The other really cool thing is that we actually improved the fit to data over lambda CDM. So we're now actually fitting data even better than lambda CDM does. Not only that, this is also detectable in future data. So this was a paper we put out in 2018, and we said, hey, ACT and SPT, two CMB experiments, will be able to observe this. Here I'm showing you the CMB, cosmic microwave background temperature, and polarization spectra for the polarization of the CMB light. Now, you can see these wiggles are not particularly visible around here in the temperature, but in polarization, you can really see that. And it turns out that the two experiments we thought would be able to see evidence of this actually maybe are seeing evidence of this. So it seems like they have some preference for early dark energy. Whether that is systematics or not is still unclear. It could very well turn out to be systematics in data that is having this preference, but it's very interesting that not only do we fit current data really well, we are detectable in future data. So I've painted a really wonderful rosy picture for you. Next, I'll tell you all of the reasons why this is still an interesting field to think about, all of the challenges we're still facing. But I'll take a moment to pause for questions again. Yeah.
So you said that your chi-square to the bit improves, but then since you're incorporating an early dark energy model, you have more number of parameters also. So
yes,
might I ask what happens to the chi-square per degree of freedom?
The chi-square per degree of freedom also improves.
Okay.
So this is a little bit tricky, and let me say a few different things why. Oops. When I said we're including a lot of data sets here, we are also including one discrepant data set, which is shoes. It's not discrepant under early dark energy, but it is under lambda CDM. So now when you're comparing a lambda CDM fit to discrepant data sets, that's not a very good fit. And if you compare that to early dark energy, which is a completely concordant fit, that's a great fit. There, the chi-squared improvement per degree of freedom is substantial, but I do not think that is the right way to compare. I would compare lambda CDM and early dark energy fit to just the concordant data sets under both models. And there we still see an improvement greater than the number of parameters we add, but not by much. I think the improvement is like delta chi-squared of 5, and we're adding 3 parameters.
So the shoes data set is a part of your fitting.
Yes.
And did you put in the shoes data set after finding out that the early dark energy model can increase the Hubble constant, or did you do it before?
So we saw that there was, oh, this is getting into like really cool territory. Okay. I can tell you a little bit more about.
Discrepant at the first, right?
Yeah.
Yes.
I can tell you about all the different reasons why we decided to include shoes into our fits. But we already knew that it was going to improve the Hubble tension, because we could see at least this effect, the stretching out of the Hubble parameter in the right direction, regardless of whether we included shoes or not. And the Hubble constant was already slightly increased. And then you go into slightly different issues of how the likelihood becomes a little bit flat in that region. So even higher H0 can easily be accommodated, but because of prior volume effect, which I can talk about if you want after this.
Right. So the only thing that I wanted to know was, even if you did not include its shoes, then also the early dark energy model would suggest the higher H0,
yes,
right?
Yes, just not maybe quite as high to solve the tension, but definitely substantially higher.
Okay.
Yeah. All right. Yeah.
So I know ultralight axions have also been proposed as sort of an alternative dark matter model, like fuzzy dark matter or something like that. And I know the mass range you quoted is quite a bit lower than even most of the fuzzy dark matter constraints I've seen. I'm just curious if you thought about combining the theories, if they fit together at all, anything like that.
That's a really great question. Okay, let me head back a little bit. No, where did I go? Oh, I'm going forward in time. I'm sorry. Okay, so specifically this potential with n, so sorry, this is 1 minus cosine phi to the n. If you set n equal to 1, that's the potential you're talking about. That is the usual ultralight axion potential that people invoke for dark matter. Now, remember how I said these early dark energies vanish at some speed? Mm-hmm. That speed depends on this n parameter. I think I have that in the next slide. Come on, go next. Yeah. So that n controls how fast they disappear. So for ultralight dark matter, n has to equal to 1. N equals to 1 worsens the Hubble tension in terms of early dark energy. So you need to make early dark energy disappear faster. Because remember, we don't want it to exist in the late universe. Mm-hmm. If it acts like dark matter, then it does exist in the late universe, because it's decaying like matter. That said, I do talk about towards the end, I do talk about combining early dark energy and dark matter and trying to see if they can play well together, but not exactly in the way that you're thinking.
I see.
Yeah.
Cool. Thank you.
Yeah. Is there another? Yeah.
So in the plot, in the graph that you were showing just before, yeah, so the energy, the early dark energy starts to decay at around the same redshift as recombination.
Oh, that's a really good question. No, it's actually the same redshift as matter radiation equality. It has to be before recombination, otherwise it doesn't. Otherwise, it won't impact the size of the sound horizon.
And is there a priori reason that both has to be the same, like, or is that informed by the data?
What do you mean that both, like, that it has to be in matter radiation equality?
Yeah.
That was really cool. We just found that in data. And now we're trying to think about why that might happen. So we're trying to think about like fundamental models of early dark energy that would include that. And I do actually talk about that in a few slides. Yeah, thank you. You guys are asking such good questions. Yeah.
Is the only effect of the scalar field to add energy, or is it coupled to other fields, and so there's more effects?
That's a really good question. Yeah. This one specifically is just adding energy. There are other scalar fields that I'll talk about in a bit that are coupled and do other funky things besides just add energy. Yeah. So this one's completely dark. It only talks to itself. All right. Okay, so we are detectable. We might have been detected, but there are challenges. What are the challenges? It's more tension. So I spoke to you guys a lot about the Hubble tension between the cosmic microwave background and supernova data. So the Hubble tension relates to the isotropic homogeneous expansion of the universe, right? But the universe is not isotropic and homogeneous. A lot of you in the room, I know, work on galaxies and galaxy clusters, voids, and all of that. So the universe has matter density fluctuations. And we can, again, measure the amplitude of these matter density fluctuations using the very early universe and a lambda CDM model. Or we can do it in the late universe, slightly more directly by observing, say, galaxy clusters, or looking at weak lensing of galaxy clusters by intervening mass. Again, these two don't agree. This is a much smaller tension, but what's interesting is that it has been growing. Right now it's at 3 sigma, and see where it goes. For the rest of my talk, I think I'd call it the large scale structure tension in case I mess that up. Either that or the SA tension. Anyway, now this is even more interesting to think about because one, maybe it tells us that we don't know how baryons work. Maybe it tells us that lambda CDM is wrong about dark matter just being simple, cold, collisionless dark matter. But the really cool thing about this tension is that we already see small scale structure tensions in lambda CDM. Lambda CDM doesn't do very well at explaining substructure within galaxies. Ask your local expert about this. I'm a cosmologist. I do not know too much about this, but it's very interesting because what's happened is large scale data sets and small scale data sets are now like covering the gap between them. And you can see tensions on both fronts. So it's pretty cool. I think it's really cool. This is what the large scale structure tension looks like. Here is the amplitude of matter density fluctuations in the late universe. And this is the amount of matter. And I'm showing you several different data sets here. You have KIDS, DES, and BOSS. And that's these contours, which pretty much agree with each other. And then you see a small tension between those and the CMB contour, which is this one, using Planck. Again, like I said, the cool thing is that as our data sets have become more precise, as people have looked for more systematics, this tension has only increased. Now, to me, this looks like a nail. I have an early dark energy hammer. I'm going to see if early dark energy fixes this. It doesn't. Early dark energy slightly worsens this tension. It grabs this contour and shifts it roughly in that direction. That quote of increase in tension at about 0.2 sigma is from, I think, about a year ago. I don't think it's too different even now, but it worsens the tension, not by too much. So this is a really confusing time in cosmology. We have the concordant model of cosmology, which has 2 tensions. I've spoken to you at length about another model, which has only one of these tensions, slightly worsened. Ideally, we need to find a new concordance model in cosmology, which has no tension. How do we do that? One way to do that is by using, say, early dark energy as a springboard, and then maybe tweak it a little bit and see if that works to solve both tensions. I'll again take a minute for questions here if you guys have any.
Just curious, how does can the early dark energy model help in solving the missing satellite problem?
That's a really good question. I guess I'll talk about it a little bit, but
yeah, I don't know much about it, but
yeah,
if there's more dark energy, then it would prevent, clustering of dark matter halos.
Yeah.
And so you could get less satellites in the late universe.
Yeah. So here's the issue with that. Early dark energy disappears in the late universe.
Okay.
One thing you could do that I have been thinking about with some collaborators is connecting early dark energy to late time dark energy, which can maybe increase late time dark energy by a little bit. But anytime you add energy density to the late universe after recombination, you worsen the Hubble tension. So you could do that at the cost of worsening the Hubble tension. One other thing that I will talk about relates to early dark energy interacting with dark matter, and that could create something interesting for structures that small. Yeah. All right. Anything else? Okay. All right. So one of the things that I was thinking about was coupling early dark energy to dark radiation. So as promised, here is what the equation looks like for a scalar field. Should hopefully be familiar to you. That's an acceleration term, that's a velocity term, which means this becomes a friction term. And then that's just the potential. So it's a ball rolling down a hill, the hill being its potential. An uncoupled scalar field only experiences Hubble friction, which is that highlighted green thing here. And uncoupled dark radiation, just like radiation, will dilute as redshift to the fourth. And that 4 is the same for here when we solve out this equation. Now, I introduce a coupling between these two by through this parameter here that appears in both equations. And what this coupling essentially does, it behaves very similarly to an object moving through a viscous fluid. So let's say I shoot an object into viscous fluid with some initial kinetic energy, right? What the fluid is going to do is slow that object down. So the object's energy goes into thermal energy of the fluid, and it loses all its kinetic energy. That's exactly what happens with our dissipative axion early dark energy here. My scalar field now dumps all of its energy into dark radiation, and dark radiation is gaining some energy from the scalar. So here's what energy density versus redshift looks like for that. I'm now showing you the scalar in blue and radiation in yellow. So my scalar starts with some initial energy and then immediately dumps all of it into dark radiation. Dark radiation gains that energy and then dilutes like radiation. So together, these form early dark energy. Again, it's described by the same parameters, how much there is, when it appears, how fast it disappears. And then for any particle physicists or model builders who are interested, the specific parameters of these equations then relate to the usual early dark energy parameters here. The really cool thing about this model, again, for particle physicists or model builders, is that it is completely independent to choice of potential. So your early dark energy comes in, as it's rolling down its potential for the first time, it just loses all of its energy immediately to dark radiation. So the dynamics of the potential just don't enter into the evolution of the scalar. So from a model building perspective, this is interesting because now this can take on whatever potential you think makes the most sense from, say, I don't know, string theories or inflatons or like whatever else you want to think about. So we've looked into this model and I can talk about this some more if you're interested. The short version is that it doesn't work. It can slightly improve the Hubble tension and slightly improve the S8 tension, not enough to solve them. And it does so at the cost of a worst chi-squared to data. So this doesn't really work. The other thing I'm thinking about is coupling to dark matter. So what you can do is say, I'm going to grab my scalar and make it talk to dark matter. So now I have an effective potential for my scalar, where it also talks to dark matter. Dark matter then gets the back reaction, where its energy density is now modulated because of its interaction with the scalar. Now, because this effectively changes how dark matter behaves, that could have implications for the S8 tension. For your question, that might also have implications for small scale structure. So you can attack a few different problems that way. The other cool thing, so Pantra's question, that this can also explain why early dark energy appears at matter radiation equality. And this is what that thing looks like. So now I'm looking at the effective potential of the scalar. Again, this is the scalar on the x-axis. In the dashed line, which I'm sorry is disappearing because it turns yellow, is the interaction with the dark matter. Again, sorry, this is the specific choices of the potential and the interaction. So this is what dark matter interaction is doing. This is the native potential of the scalar. And then the solid line that you can slightly see is the effective potential. So now the scalar is rolling in its effective potential. It is released close to matter radiation equality because of its interaction with dark matter. And yeah, so that's something I'm still trying to think about and see whether this helps both the Hubble and the SA tensions. I can talk about this some more, but in the meantime, for now, I'm just going to summarize and open it up for questions. I've told you about two really interesting questions in cosmology. It's very important to continue to ask whether they are real. But if they are, it's also very interesting as a theorist to think about what kind of new physics could they be pointing to. Hopefully I've convinced you that solutions to the Hubble tension lie in the early universe. We have to modify the early universe to solve the Hubble tension. One of these examples is early dark energy. It can, several fundamental models can form early dark energy, it resolves the Hubble tension, and the fundamental physics of the model dictate how well we're solving the Hubble tension and how well we're fitting data. So it's worth it to explore several different early dark energy models. CMB data that is current and upcoming can not only detect early dark energy, but right now seems to indicate some preference for it. Of course, early dark energy faces some challenges with large-scale structure tension, but it did not create this tension. This tension already exists within lambda CDM. And maybe we can use it as a springboard to search for a model that solves both tensions. So I've spoken to you about one that I'm still thinking about, early dark energy interacting with dark matter, and another one that doesn't quite work, early dark energy talking to dark radiation. Finally, it could be that these two tensions require two different solutions. They're very different because the Hubble tension is about the isotropic homogeneous expansion of the universe. The large-scale structure tension is about the perturbation evolution of the universe. This is not a very exciting possibility. As a theorist, I crave elegance, and this is not very elegant. But in the meantime, I will leave you with the thought that it's time to get creative with dark sector physics. Thank you for listening to me.
Thank you very much. We still have some time for questions, although there is many questions.
Just speculating here. So since you said that what do you call it? Sound horizon. Okay. You early dark energy makes the same happen at earlier times. Right.
Yeah.
So I'm just wondering, is there any direct way to measure the optical depth to recombination and test this observationally?
It's a really good question.
Because if it's happening at an earlier time, then the optical depth should increase.
Yeah. I don't know if there's necessarily a very direct way of doing it. There are a few indirect ways that I can think of. If we were to get, I'm not going to bother going all the way back. Okay. Observations during the dark ages, so 21 centimeter observations. This is highly theoretical. If we can push that all the way back to like the redshift of a few hundred, then that might tell us something, because if we can like see what the universe is doing at that time, what structure is doing, that might give us a very indirect way of seeing how early should recombination have happened. Another really indirect way of, actually, let me not go into that. That's too complicated. The other thing I'll just say is early dark energy doesn't actually change things by much. The amount that you have, it's a very small little bump in H of Z, and then very rapidly vanishes. It's a 10% effect. Getting those measurements down to 10% would be really hard. The most precise measurement we have of the universe is that angle that I kept talking about in the cosmic microwave background, and we measured that to sub% levels. It's excellent, but most other measurements are not that good. I can't think of anything which would give us like a more direct way of doing that. Yeah.
Yes, I guess you showed data showing a 3 sigma, I guess, preference for variable dark matter and dark energy models. Can one turn that statement around and say that to 3 sigma constant dark energy models like lambda CDM are disproven or disfavored, dispreferred?
That's a really good question. I don't think at 3 sigma I would throw out lambda CDM. I certainly wouldn't until I understand exactly where the preference is coming from. From what we've seen so far in ACT and SPT papers and what we've been looking at ourselves, like folks who think about early dark energy, is that it's only a few data points in the polarization spectrum of ACT, at least, that is giving us this preference. I would not stake the claim of detection on those few data points. My threshold for actual detection of early dark energy is very high. 3 sigma certainly doesn't cross it. Certainly not until we understand why ACT and SPT have differences between their measurements and Planck's measurements, because even that is above the 2 sigma level. Like ACT and Planck prefer very different NS. Don't quote me on this, but I think it was either 2.5 or 2.7 sigma different. So yeah, unless we understand those, I don't think you should read into it too much. Yeah.
In your model, you mentioned how the density of the early dark energy stays the same until right before recombination. So before that point, is there a reason why it stays the same despite the expansion already happens?
Yeah, it's a good question. So that goes into the physics of cosmic scalar fields. The right way to actually think about this is that the field is actually slowly rolling the entire time throughout the history of the universe. And its rate of rolling is several orders of magnitude slower than the Hubble rate. So the universe just doesn't notice that the scalar field is rolling. Once the rate of rolling of the scalar field matches the Hubble rate, that's when you actually see, oh yes, it's now gone down. It's the same argument as, if it helps you to think about it, as dark matter decay rates. Let's say I have dark matter whose half-life is, I can't think of numbers anymore, a giga-year, okay? So until the universe is 5 giga-years old, I'm not really going to notice a difference in dark matter. I certainly wouldn't when the universe is only like 1 million years old. Does that make sense? So it's the exact same principle. The rate of change of the scalar field is so slow that the universe doesn't notice it, and that's why we call it frozen, but it is really slowly rolling the entire time. Once the Hubble rate matches the rate of rolling, that's when you suddenly see it released and it does the little oscillations.
Just a follow-up, if the inflation model is correct, how does your early dark energy fits in that period?
Okay, those are a few different questions. Let me answer all the questions I think you're asking. Inflation and early dark energy don't talk to each other. So inflation can do its own thing, and those constraints will have no impact on early dark energy. But early dark energy would be a spectator field during inflation. So what that means is, usually when we think about inflation, we think about this inflationary field came in, the universe inflated, and then the inflationary field reheated the universe. So it created all of the different particles that we have in the universe. Because all the different particles were created by the same field, their density fluctuation profiles are all the same. Does that make sense so far? Okay. If this field is a spectator during inflation, this field already exists regardless of what the inflationary field is doing. Its density fluctuation profile will be different from all the other stuff in the universe. That is something you can independently try and constrain. It's very, very complicated. So we solve this problem by not thinking about it. Yeah.
Yeah, so when you were talking about using ACT and SPT to indicate preference for EDE.
Yeah.
I was wondering, you're directly measuring CMB, right? You're not using either of the telescopes to measure, say, to try to detect the number of clusters using a SE effect to see if their abundance matches the predictions from early dark energy, right? Because there have been, I guess very recently, I'm not even sure if the papers are published yet, but there are some like N-body simulations based on early dark energy cosmology. And I think they have found that at redshift 10, they will produce way more massive dark matter halos compared to lambda CDM. And the difference just decreases as with cosmic time. And at redshift 1, I think that might be like 10 to 20% more clusters than the lambda CDM. And in the local universe, they're identical.
Yeah, okay.
So maybe not identical, still like 10% difference, but I think maybe you can just use those telescopes to use SE effect and like try to find out if the number of detected clusters are consistent with either early dark energy or lambda CDM.
Yeah, that's really interesting. So we have only been using those data sets in terms of CMB. We haven't used any SE stuff.
Oh, okay.
The reason that early dark energy predicts more halos is because it's not anything that early dark energy is doing. It's because when we mix that and change all the other cosmological parameters, we want significantly higher dark matter in the universe. That's where the extra halos come from.
Gotcha.
So if you can independently tell me dark matter cannot be more than this amount, then that will constrain early dark energy like immediately. So you can still use the SC clusters, I guess, and tell me we can't have more than this much dark matter. And then I will go out and say, okay, great. So then we can only have this much dark energy.
Yeah. Thanks.
Yeah.
Does the early dark energy also alter the primordial helium fractions?
That's a good question. It doesn't really. We have some very small impact to omega baryon, but negligible, certainly negligible in terms of primordial abundances of elements.
All right, we've had lots of questions. Quite amazing. Well, thank you again. And we will be around tomorrow as well. There are probably still some open slots in the morning. If you want to continue conversation or ask more questions, do sign up and perhaps also send an email because it's late in terms of signing. All right.
Please send me an email. Thank you.
Thanks.